Okay.
All right, so we'll go ahead and get started. Please remember to sign in to the chat. So we've got you recorded. And otherwise, we will continue on. I know Monday is a little slow. I'm sure I'm not the only one, so we won't hopefully get too crazy. We will see. All right. So we've been going over a long time ago. We've been going over functions and talking specifically about graphs of functions and what it means to do certain things within a function. So recently we've been talking about transformations. And the idea here is we take some simple parent function and we create any other kind of function from that parent. Simplest version of these is for a line. So y equals x. This is a parent function for linear functions, meaning you can take this linear function and you can transform it to make any other one. So most notably right now, the slope is what? What is the slope of this line? What is the slope of that one? Final's gonna be tough. Slope is 1. Y-intercept is 0. So these are the kinds of qualities that we're going to end up changing with these transformations. One kind of transformation that we've already talked about is a shift or slide. In order to perform a shift or a slide, this same idea underpins all the other transformations we're going to do. So I suggest you come to terms with it. But we talked about, instead of moving the actual line around, what we do is we shift or slide the graph paper underneath the line. The way we move the graph paper is by moving the y or the x, or sometimes both. So if we want to move the line up, that would be the same thing as moving the graph paper down. If we want to move the line down, it'd be like pushing the graph paper up. So you take whatever you want to do to the line, and you do the opposite to the graph paper. So if we want to slide this thing up, then we take our y values, and we are going to subtract something from them. So this is the same thing as pulling the graph paper down underneath. We want to move the line down. We're going to add or shift the graph paper up. And same thing with the x values. All right. All right. So this is what we talked about last time. This idea of shifting the graph paper. Well, let's look at what that actually means algebraically. We take the line y equals x. And if we shift that line up by, let's say, 3, then what happens? Well, so we moved it up 3. The y-intercept went from 0 up to 3. Well, let's look at algebraically what actually happened to do that. Because it says that if we go up, we need to subtract something from y. We have y equals x. And so then we go to y minus 3 equals x. If you resolve this for y, you get y equals x plus 3. So by changing the y value, and at the end when you resolve for y, you get the new correct equation for that. Same thing if we move it to the, let's say, the right by 2. So we want to go from here out to here. So the equation for this line is what? I'll wait on this one.
Is it y plus 2? Or x plus 2?
So the slope is still 1 because these don't change the slope. But what is the y-intercept of the green line? Where does it go across the y-axis?
Yes. No, she wasn't. No, she wasn't. Not at all.
So which way do we move it? To the blue line, we moved it to become the green line. Which way and by how much did we move it?
Moved it right by 3.
Right by 2.
We went to the right by 2. So if you go to the right,
So it's x minus.
everywhere you have an x, you put x minus however much you moved it. So this was the original line. This is the with the shift in it. So what is the y-intercept of that line?
Zero.
Nope, it's not 0. Y equals mx plus b. B is the y-intercept. So what is the y-intercept in this equation?
Not sure if I got scaling right, but I want to say that looks like a 3 or 4.
What's the number that's being multiplied by x? What's the number in front of x?
1.
1. What's the number being added to x? Not 2. It's -2. So the y-intercept is -2. Whew. All right. So this is how transformations work. you're not into understanding them, then you can at least just follow the rules. That whenever you shift up, you take your y and you replace it with y minus however much you're going up. If you're going down, you replace y with however much with y minus. I'm sorry, plus however much you're going down. To the right, you replace x with x minus however much you're moving. And if you're going to the left, you replace x with however much you're moving to the left. So, yeah, these are the shifts, the translations. This is not terribly difficult, but it's feeling like a Monday, I guess. So we will just continue on. There is another thing that you can do with graphs. And it's not a very simple, it's not as simple as pushing it around. But mathematically, it's very simple, like pushing it around. So this is our graph. Let's see. What kind of line do we want to do for this one? Oh, so this next kind of transformation that we're going to talk about is very, like I said, as far as physically doing it, it's not as easy as just we're pushing the thing up or down or left or right. But mathematically, it's very simple. So one of the things that you can do to this is you can flip it or you can reflect it over some axis. So let's look at that for a second. These are called reflections. And one of the things that marks how a reflection works is that there's something is preserved in this transformation. The idea is that very basically there is some line that acts like a mirror, and the graph looks the same on one side of that mirror as it does on the other side of that mirror. Just like if you have a mirror, and you're looking at the mirror, your bodily proportions and everything are maintained, but something does get flipped around. Usually people look at it as their handedness. If you hold out your right hand, then your reflection is holding out their left hand. But they are looking back at the mirror as well. So when you look at the mirror, you see somebody looking back at you, and vice versa. So basically what we've done is, if we didn't have this side, we took this side, took a picture of it, and we spun it around and laid it down on that side. So this is what we do with a reflection. We take this red line and we're going to flip it. On this one, we'll do it over the x-axis. So if we flip it over the x-axis, we're going to get something that looks like this. And when we do that, so we started off with y equals x squared as our graph. And can anybody take a guess what the green one, what that equation is going to be?
Under the impression of reflections, I'm assuming it'll be the same thing, but it'll be negative.
It'll be negative. Yeah. So this is y equals negative x squared. So very good. How do we do that? Is there something that we did that we can repeat every time and have some sort of setup that every time we want to do a reflection, we can do this? This is what math is kind of all about, is taking something and generalizing it so that every time you try and do it, you have a simple process. So if we look at what we used the last time, we said that in order to do a shift of the graph, what we actually do is we shift the coordinates of the graph paper underneath it. So when I do this, what I have to do to the graph paper to make it do this thing? So we're going over the x-axis. This thing goes from this point down to here. This one goes from here to here. And this one just goes from there to there. So what we're doing is we want the top of the graph is currently at the positive end, and the bottom of the graph is at 0. But we need to move it around so that the left side of the graph is still near the negative x. See, this is still near the negative side, and this one is still near the positive side. So what we're doing is just taking the graph paper and flipping it face down. What that does is it takes the positive y side and switches it with the negative y, but it doesn't change the negative x and the positive x. So what this does is flips it over the x-axis. And the process by which we do that looks like this. So we're flipping it up and down. So we're going to change the y variable. So y goes to negative y. So we take our initial function, y equals x squared, and we transform it to negative y equals x squared, and then we resolve for y. So we get y equals negative x squared. Okay? So same idea as before. Whatever transformation we're trying to do it to the variable. And in this case, if we're flipping over the x-axis, then we have to flip the y variable. Or if you're reflecting over the y-axis, what are you probably going to do?
Wouldn't the x and the y switch places in the equation?
No. So if you reflect over the x-axis, remember you're doing the opposite. So you have to flip the y variable. If you're reflecting over the y-axis, you flip the x variable. But you do bring up a very interesting case, which is going to be our last reflection. So if you're going to reflect over the x-axis, you switch the y variable. If you're going to reflect over the y-axis, you switch the x variable. Well, there's a special kind of reflection that does something a little bit different. So I think Mr. Peterson, what did you suggest for that last question? You had an answer? What was it?
That in the equation with x, when the y and x switch places, so that the x will be like x equals positive or negative not positive or negative y.
Yeah.
The power.
So you said that the x and the y's switch places. Now this is different from the other two that we were talking about. The other two, we had so in the other two, we changed the y to negative y, or the x to negative x. But what we didn't do is go outside of the x's or the y's. So let's take your answer and work backwards and try and figure out what does it mean if we switch the x's and the y's. So if we switch, then y becomes x, and x goes to y. What about negative y? So if you're switching them,
negative x.
yep. So technically you only need the first two and the other two are implied, but for this purpose, it's a little bit better to go ahead and show it like this. So what would we have to do to the graph paper to do all of those things? What would we have to do to this thing So on the previous one, we took, when we did a reflection over the x-axis, we took the two y's and we flopped them, which is the same thing as taking the graph paper and flipping it over. If we switched over the two, over the y-axis, we would switch the two x's, take the piece of paper and flip it over. So what are we doing if we do all of these, though? How are we flipping it? So where does y go?
The x. Wait a minute. Is this rotating?
I'm sorry?
Is it rotating?
I can't hear you.
No, like, is it rotating?
Well, they were all rotating, right? So this rotates this way. This rotates that way. We're trying to figure out how does this last one rotate. So y goes to x. What is...
So it's rotating clockwise.
No. Where does x go?
Y?
x goes to y. So what about negative y? Where does it go?
Negative x.
It goes to negative x. Where does negative x go?
The y.
To negative
Negative
y.
y.
So it's rotating across a line that goes this way. So it goes from here to here, or here to here. Doesn't matter. Point is, where is the line of rotation? So what is the line? And it's drawn off a little bit, but what is the line, the equation of that green line, if it goes to the middle? It's actually that. It's the equation of that line. Probably going to get